Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to look at some acids and explain why the acids might be more acidic than we would normally predict. So let's get into this. Okay, so in this problem we're told acids are molecules that give up protons. Proton is another word for H plus. H plus is the hydrogen with the one electron removed. So a normal hydrogen atom has one proton and one electron, so it has no charge. But if you take away the electron, you're left with just the one proton, so it has a plus charge. So we call it a proton. So acids are molecules that give up protons or H plus ions. A strong acid more readily gives up a proton than a weak acid. Draw a Lewis structure for each of the molecules shown below. Use the stability gained through the modified molecular orbital theory to explain how each of the molecules below could behave as better acids than you might normally have predicted. Okay, so let's start with the the molecules, of course. So here we have our molecules, and so they want us to draw the Lewis dot structure. This oxygen is double bonded to this carbon. This oxygen is bonded to the carbon, so that's what this means here. Same thing here. This carbon is bonded to that carbon, and the oxygen is bonded to the carbon. And so the asterisk here is indicating what hydrogen is the acidic hydrogen, which one's going to be taken off. Okay, so I drew the Lewis dot structures here. So here's the formula, here is the Lewis dot structure. And so when we're using the modified molecular orbital theory, what that means is you can use valence bond theory to describe the sigma bonds, but then you can use the molecular orbital theory to describe the pi bonding. So the valence bond theory takes care of the localized electrons in the sigma bonds. The molecular orbital theory that can take care of the delocalized electrons in pi bonds. So when we're looking at the molecules, so when we're looking at this one, here we have sigma bonds, and then when this double bond indicates a pi bond, you have a sigma bond and a pi bond. And so when we're looking at the hybridization, we can see that this is sp2 hybridized because it's got 3 electron groups. And so that's going to have a trigonoplanar structure. And then this oxygen, according to the way it's drawn here, has sp3 hybridization. However, this oxygen can also form a double bond because there's resonance here, right? So this has some sp2 characterization. Okay, so what I mean by this is what could happen is the electrons in the bond here can add to the oxygen, adding a third, how should I say, a third lone pair. Sorry about that. Not a lone pair on the oxygen. So the 2 electrons here can go and form a double bond here, breaking this bond here, giving off your H plus ion. But then this carbon would end up with 5 bonds, which is not possible. So that's going to push the electrons in one of the bonds here onto this oxygen, giving it 3 lone pairs and a single bond. So then this oxygen would have a negative charge on it. And then this hydrogen would be attracted to this oxygen and then bind there, right? So you could have the OH group here instead of here, right? It would still be the same structure, except the hydrogen would be bonded to this oxygen rather than this one, right? So you got some delocalization here. And so you could use molecular orbital theory if we see this carbon as being sp2 hybridized and trigonoplanar, this oxygen is sp2 hybridized, and then this oxygen would be sp2 hybridized with only one lone pair. And so if you take the lone pair, then it would be sp2 hybridized. That means that each of these each of these atoms would have an unhybridized p orbital, and you would have 4 electrons left over after the sigma bonding. So if you count the sigma bonds, you have 1, 2, 3, 4 sigma bonds. That's 8 electrons, right? So then you would have 2 lone pairs here. That's 12, and 1 lone pair there. That's 14. But the total number of valence electrons is 18. So that leaves 4 electrons not accounted for. Those 4 electrons could be in the 3 molecular orbitals that are formed. And if you saw my other videos, most likely this is going to be the molecular orbital energy diagram, where you have pi, non-bonding, and then you have the pi anti-bonding molecular orbital. So you have 4 electrons, so 2 would go into there, 2 would go into there, and then that's it. So doing the bond order, if you were to calculate the bond order for this, it would be the number of bonding electrons, right? So bond order equals the number of bonding electrons, which is 2, minus the number of antibonding electrons, which is 0. We don't have electrons in the antibonding orbital. And although we have electrons in the non-bonding orbital, those don't matter. They're not going to influence the bond order. So then it would be, we would subtract out the antibonding electrons and then divide that by 2. So that would give us a bond order of 1. That would give us 1 pi bond. And that's what we see here. But in this case, the pi bond is shared equally between the atoms. So it would be half a pi bond. So the bond order would be 1.5. 1 sigma bond plus half of a pi bond shared between here. But the pi bond is described by the molecular orbital theory. So here, I guess the upshot would be, if you have resonance, that resonance, without referring to resonance, we can talk about the bond order due to the electrons in the molecular orbitals. And so there's delocalization here, and that delocalization of the electrons in the pi bond allows for this to be more stable. This oxygen is more stable. The ion is more stable when you get rid of the hydrogen. So if I get rid of the hydrogen here, the leftover anion is more stable without the hydrogen than you would expect, therefore making this an easier, I should say, a stronger acid. It more easily gives up the proton than you would normally think because of the delocalization of the pi bond electrons due to molecular orbital theory, or as explained by molecular orbital theory, and as we can understand from resonance. So same thing here for this molecule. Here's our hydrogen. This is the acidic hydrogen. Now this is an alcohol group, and you would not really expect alcohols to be acidic, right? They don't typically give off their hydrogens, but in this case, because you have this structure, notice you have single bond, double bond, single bond, double bond, alternating pattern here. And so if you see that, that is what's going to make this oxygen, when you give off the hydrogen, the H plus, so this is going to become H plus, right? So then you're going to be left with a negative ion in the rest of the molecule, and that's going to be more stabilized because of the structure here. And again, that's going to lead to this being having sp2 character or trigonoplanar structure. And so you can see that this carbon has sp2 hybridization, this carbon has sp2 hybridization, this carbon has sp2 hybridization, and this oxygen has sp2 hybridization. And so they all have an unhybridized p orbital, right? So that's going to allow for the unhybridized p orbitals to interact with each other to form molecular orbitals. And then the electrons that are in those molecular orbitals can then be delocalized, and the electron density is shared along all of these atoms. And so that's going to stabilize this molecule. Let me show you what I'm talking about here. So what could happen is the electrons in this bond here could then be moved to create a double bond there with this carbon. So this hydrogen would break off, becoming positive because it lost the 2 electrons. It forms a double bond here. And then this double bond here would have to move here, forming a double bond there. And then this double bond here would have to break. So a pair of electrons here would have to go onto this oxygen, making this a single bond and having 3 lone pairs. And then it could go back. So the electrons could go backwards. So you could do the arrows backwards. And so that allows this delocalization of the electrons, and that can be explained by molecular orbital theory, right? Because we have 1, 2, 3, 4, 5 unhybridized p orbitals. You combine those together, you get 5 molecular orbitals. And so you fill in the electrons with those molecular orbitals, and you find the number of pi bonds, the bond order, and then that bond order is shared among the atoms here. So because of this resonance that you see here, that's explained by molecular orbital theory. And so that's going to stabilize the negative here or here. So this anion is more stable once it loses its hydrogen than you would expect. And it's the stability of the anion that allows it to more easily give off the proton. So it becomes a stronger acid than you would expect. And then finally, same thing here. This is our benzene ring again. We've seen this in previous videos. So again, your typical benzene is you got your 6 carbon ring here. You've got double bonds here. These double bonds can move, right? So this double bond can move there. This double bond can move there. This double bond can move there, right? So the double bonds can move. So all of these carbons are sp2 hybridized, meaning that every carbon here has an unhybridized p orbital. And each of those carbons will have 1 electron in there. And that's going to allow for the interaction or combining of those atomic orbitals to form molecular orbitals. And then those electrons can be delocalized among the carbons. Also, notice here that, again, this hydrogen, the bond can break. These electrons can move here, forming a double bond between the oxygen and carbon. And then because that would give that 5 bonds, then what would happen is that would be 2 bonds there. So this bond would have to go there, and then you'd have a double bond here. And then this bond would have to move there, and so on. So you got the delocalization there. And so then again, because of the resonance that you can get with this molecule, this negative charge on the oxygen after it releases the hydrogen again, that negative anion that's left over becomes more stable because of this sharing or delocalization of the electrons because of the molecular orbitals that are formed from the unhybridized p orbitals that are left on the oxygen here, as well as the 6 carbons. And so that explains the stability of the anion that's left over once the hydrogen leaves, and it's that stability of the anion that allows for the molecules to give off that hydrogen more easily than you would have expected. So that's it for this video. I hope that explains why these acids are better acids than you might normally have predicted based on what we know of resonance and molecular orbital theory. So that's it for this video. I hope you enjoyed the video. I hope you learned something from this video. If you did, like the video, share the video, hit that like button somewhere over here. Also, subscribe to my channel. Help me out. Hit that notification bell. When you do that, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Let me know if you have a problem or question you need help with. Let me know if you have a topic you want me to cover. I would like to do that for you. Thanks for joining me and have a great day.